In this video, we'll walk through a systematic approach to designing logistics systems, particularly intralogistics systems, grounded in structured data analysis and principles of systems engineering. The graphic you see on this slide outlines a four-stage process, moving from raw data input through analysis to actionable results and ultimately toward a conceptual design. It is an iterative approach, reflecting the fact that logistics system design is rarely linear. Instead, we move back and forth between stages as our understanding of the system deepens. Stage 1. Input data. We begin with the input data phase, which involves the identification, collection, and structuring of all relevant datasets. This includes master data. This encompasses fundamental, relatively static data such as SKU lists, item dimensions and weights, unit of measure, packaging hierarchies, supplier information, and storage requirements. High data quality at this stage is non-negotiable. Errors in master data can propagate through the entire analysis chain. For instance, inaccuracies in item dimensions directly affect storage calculations and throughput modeling. Well, I just said high data quality at this stage is non-negotiable. Frankly, anyone who has done data analysis before will roll his eyes now. Reality is, quality of master data frequently is not great. In fact, it often is poor. Sometimes the data is so bad as to be outright useless. There are different reasons why this often is the case. One is that in an organically grown, manually operated system with a stable workforce and a few individuals who know by heart all the details of the business, accurate master data isn't so important because nobody ever uses it for any analysis. But it does become important the moment you're considering automating your system, and you need to understand whether a product fits into a plastic box, and if so, how many pieces of it. Also, it is important to understand that while some companies maintain high-quality master data, it is a rare exception to come across a set of master data that does not have some flaws at least. So you have to expect some uncertainties, and you will have to make some assumptions. More about this later. Next, order data, or more generally, transaction data. This is where the dynamic part of the system comes into play. One important question to answer here is how much order data you want to analyze. And the answer is just enough to get representative time profiles out of it. This can be tricky if the business is characterized by strong growth or by a strong seasonal profile. The latter case can be addressed by getting at least a full year of data. Depending on the size of the business and on the size of your CPU, this can be an amount of data that may bring your computer to its limits. Doing extensive data analyses with millions of lines of data requires either patience or a powerful workstation, and forget Microsoft Excel in this case. If getting a full year of data is not an option, or if the data is too extensive, you may want to get something like representative averages to understand baseline operations and peak times, which are critical for capacity planning. Another important dataset is growth data. Long-term system dimensioning requires some form of growth projection. This can be based on historical trends, forecasts provided by sales or product management, or even strategic plans. These data points are necessary for sizing the system, not only for today's requirements, but also for future. Consider the time gap between the data you analyze, that might be a year old by the time you analyze it, and the go-live of the system that you're engineering, which may be a couple of years down the timeline. In order to make sure that the system you plan isn't too small by the time it is ramped up, it is important that the client you are working with provides some indication of growth for picking orders as well as SKU count. Also, we need operating hours and shift models. These define the temporal structure of resource availability. A facility operating in a one-shift system will have very different resource and throughput profiles compared to one working in a 24/7 environment. Consider that in e-com, many customer orders come in the late afternoon or evening hours, as well as on the weekends. In other words, customers order when they are at home, not at work, just like the warehouse staff that's supposed to process those orders. This implies that in one-shift operations, there is an offset between order arrival and order processing. In three-shift operations, this is not the case. For many projects, we also need inventory data in order to be able to assess the storage needs of the future system. And depending on the project, we may need additional data sets, such as return rates, replenishment patterns, supplier arrival times, and so on. When you intend to analyze data on behalf of a client, it makes sense to provide some guidance as to the data scope and data quality needed. Many companies have never pulled this kind of data from their systems, and they will be helpful for any assistance. Stage 2. Data preparation and data analysis. Once we've collected the data, we shift to data analysis. First, we upload and clean the data, standardizing formats, fixing inconsistencies, and checking for completeness. Tools like Python with Pandas or Power Query help us spot outliers, null values, and structural issues. Please note that best practice is to always maintain an unmodified version of the original data files. For one, you should have a backup in case you get something wrong. But also it is important that you are able to demonstrate how the original data looks like that you received. In case there are errors in the results of your analysis, you want to be able to trace them back, either to the original data set or to the way you transformed it throughout your analysis. So simply write protect the original files. You can upload a cleaned version to your database for quicker processing. Then we perform quality checks. This isn't just checking for missing values. It's about validating business logic. Are there SKUs with negative inventory? Orders with zero quantities? We need to catch these before drawing conclusions. Next, we merge datasets, connecting order lines with SKU master data, for example. This allows us to analyze not just order volume, but volume in combination with size, weight, or storage category. We then query subsets like all items picked more than 1,000 times per year, or all orders with more than 5 lines. These queries help us tailor design decisions to real operational segments. Throughout, we use tools suited to our skills and project scope, from SQL databases to Jupyter notebooks, from Excel pivot tables to Tableau dashboards, or Power BI. You can use whatever you like. My personal favorite is Python with Jupyter notebooks, due to its versatility. Stage 3. Results from data to requirements. From this analysis, we derive design-relevant results. These form the bridge between data and concept. Let's break these results into two types, dynamic and static. Dynamic requirements capture how the system behaves over time. We build time profiles of picking, shipping, or inbound deliveries. These reveal peak hours, daily cycles, or seasonal patterns. We analyze the order structure. For example, do customers typically order single items or 20-line orders? That makes a huge difference when choosing a picking method and determining requirements for the automated system. More about this later. We then match our findings to appropriate technologies, maybe batch picking in manual zones, or goods-to-person systems for low-frequency items. But also, the size of items and temperature requirements play an important role. We perform ABC analysis and related analyses to classify items by movement. Class A items, the high runners, often go into high access zones. Class C items can be stored in less accessible areas. On the static side, we calculate required storage space. This is based on average and peak stock levels, pallet types, and turnover frequency. These requirements give us the building blocks for the next phase. Please note, these results provide the essential backbone of any warehouse design, but in practice we often perform additional analyses, like XYZ analysis for consumption variability, consistency analysis, or shopping cart analysis. Stage 4. Concept from requirements to design. Armed with our requirements, we begin sketching the system concept. First, we build a material flow diagram. This shows how goods move through the warehouse, from receiving to storage, picking and shipping. It helps us see bottlenecks, crossings, and flow distances. The material flow diagram may be the most important outcome of the entire engineering exercise. Then we sketch the storage systems. Based on item profiles, we decide between pallet racks, flow shelves, and so on. And of course, we define the picking concept. Whether we use single order picking, zone picking, or goods-to-person automation depends a lot on the order structure and throughput goals. This conceptual design isn't the final blueprint, it's a first draft. And often it reveals inconsistencies in our assumptions or data. That's why the process loops back. We revisit earlier stages, refine our analysis, and adjust the concept. And then, of course, there are several constraints we have to consider. There are quantitative constraints, things like floor space, budget, and staffing limits. They're measurable. There are also qualitative constraints that are harder or impossible to quantify. Things like ergonomics, safety policies, or corporate sustainability goals. But they are just as real. And often they are the reason we choose one solution over another. Designing logistics systems means navigating these constraints, and at the same time balancing performance and cost.